Hi, my name is Haochen Huang from UC San Diego. Welcome to my talk about our work on protecting data integrity of web applications with database constraints inferred from application code. Database-backed web applications are widely used in e-commerce, social, banking, and many aspects of our daily lives, and they have critical requirements on data integrity. Here shows the common flow how data gets into the database. The user submits a request, then the request is handled by the backend application code. And the app issues some database queries to insert the data. The data here needs to meet some business rules, such as user's name cannot be none, or the email need to be unique. Unfortunately, we commonly see bugs in the application code and insert the data that violates the rules. And it could lead to severe consequences, such as crashing the page and corrupting the order and user data. Fortunately, we notice that most of today's relational database supports integrity constraints. That is, developers can specify the constraints based on their business rules and enforce them in the database schema. When there is any incorrect data manipulation caused by either bugs or operator mistakes, the database will detect and block it. Therefore, to fix the problem and more importantly, to avoid similar issues in the future, developers added the database constraints. So why using database constraints? Many developers think that their application code is enough to do the job. However, such assumptions often fail in practice. As the figure shows, database data can be added or altered in various places in the application code. Some of the places may even be outside the app, but from batch scripts or DB console, which bypasses all checks in the code. It is difficult to ensure that every single place has proper checks. In comparison, when constraints are enforced by the database, even if validations are missed in some passes, the database always acts as the final gatekeeper to perform integrity checks and block violations. Therefore, we believe that web apps should take full advantage of database constraints to ensure data integrity when possible. Before we work on the solution, we first aim to understand more about the current status of database constraints. We studied the added constraints in commit history in 5 popular web apps. The first observation is many constraints for each application are added as afterthoughts, which means they are missed first when the columns are first created and added later in another commit. We further study how developers notice these missing constraints in the first place. Besides those added by the new features or code refactoring, a majority of constraints are noticed related to reported issues, making missing constraints a real problem with consequences. The third observation is most of the issues miss validations in application code as well. Either there's no validation at all, or they miss in some code passes. The study shows that even for these widely deployed web apps, database constraints are not fully utilized. So, can we build a tool to help developers automatically identify the missing constraints? There are 3 possible approaches. The first is letting developers inspect the whole database schema manually. It requires huge efforts and is error-prone. Another approach is to infer from the production data. For example, if a column has all 1 million records being unique, a potential constraint is indicated. The idea is intuitive, however, it has 3 main limitations. Approaches based on stats are usually biased and limited by insufficient datasets, especially for newly created tables or columns. This approach also has high false positive rates. For developers, gaining access to the production data has privacy and security concerns. The third approach is to infer constraints from the application code. After looking into several real-world web apps, we observed that code contains many patterns with hints for database constraints, because the developers have the assumptions about data constraints in their mind when coding. So we choose to build a tool called cFinder to infer missing database constraints from the application code. It has 3 steps. First, we recognize the code patterns that have assumptions on DB constraints. With observed patterns and application code as input, the tool traverses the code to find a match of the pattern. Third, from the matched code snippets, we use analysis to extract the formal database constraints. The final output is the set of DB constraints. First, I will show some examples of code patterns we observed that have assumptions on each constraint. Let's look at a real example for uniqueness. For a table wishlist line, there are 2 columns storing product ID and wishlist ID. It only allows one product in one wishlist. So here, product and wishlist are composite unique. Let's see the code when you save a new record. Before saving, the code first retrieves records filtered by product and wishlist. Check if that record already exists, and only saves it if no existing record returns. One code pattern we summarize here is check existence before save. It reflects developers' intention on uniqueness. Only one record with the value can exist. Here is one example for not none constraints. The code invokes a field or method on a column, line.parent, indicating that the column should be not none. Otherwise, invocation on none will throw an exception. So we summarize it as a pattern and further refine the pattern to exclude cases that have explicit non-checks before the invocation, as the check will make it a false positive. Here is an example for the foreign key constraint. In the code, the primary key value from voucher table, voucher.id, is saved to discounts column named voucher ID, indicating that the voucher ID should be a foreign key to voucher. It reflects the referential assumption between tables. The columns in the dependent table refers to the primary key value in the reference table. We list all the observed patterns for each constraint types here. Please check the table for more details. After observing the code patterns, the next step is to traverse the code and find the matches of the patterns. We summarize 3 types of conditions that need to satisfy. The first one is syntax pattern matching. Let's first look at the blue circles. We aim to match the code snippet with the pattern of saving a record. To do this, we predefine a category of syntax patterns that have that meaning, called psave. Then we turn the code snippet into the AST. Then we traverse the AST and find a match of psave. Similarly, we match the other subtree in AST that checks for the existence in the red circle. The second condition requires the subtrees to follow certain control dependencies. That is, in AST, the 2 trees should be under the correct branch of the if node. Third, for data dependency, we require that the variables in 2 subtrees refer to the same table and columns, so they are checking and saving the same data. The third step, this step is to convert the matched snippet into formal DB constraints. That is, identifying which table the variable represents. This is often non-trivial. We use the useDef chain analysis to find the class definition and use the table's metadata to check the foreign key reference. I'll skip the details here. Next, evaluation. We evaluate the effectiveness of cFinder based on how many new missing database constraints can be detected. We then evaluate the precision and coverage of detected constraints. Please check the paper for more evaluations on performance and developers' feedback. We evaluate the tool on 8 web applications, including 7 widely adopted open source web applications and 1 commercial company. They all have high requirements on data integrity and reliability. This table shows the number of detected missing database constraints. In total, CFinder detects 210 new missing constraints and another 16K constraints that already exist in database. So far, we reported 92 of them and got 75 confirmed by developers. Next, we evaluate the precision. We have 2 inspectors manually label them. The precision is reasonably high for all 3 types of database constraints. 82%, 75%, and 80% for unique, not none, and foreign key constraints. In total, 34 false positives are introduced. 12 are caused by the static analysis being unsound, and 13 are caused when code matches the pattern but contains no assumption on constraints. The reported false positives will not cause a big impact and can be easily recognized, because developers can check the code snippet that implies a constraint. They can also easily cross-check with the production data. Even if they wrongly add a constraint, the database will reject the schema migration if any existing data violates it. Developers can then decide whether this is a false positive or if data cleaning is required. We then evaluate the coverage. We have 2 different datasets. The first one is from our study, the missing database constraints from the schema migration history. It can detect about 80% of them. The second dataset is the existing constraint already set by developers in the current database, and we can detect 75% of them. To summarize, we help developers utilize database constraints to protect the data integrity of their web apps. We conduct a study to understand the current status of missing DB constraints. Then we build a tool to detect 210 new missing constraints with good accuracy and coverage. So far, we have reported 92 of them and got 75 confirmed. Thank you.